Now we're good? Okay. All right. So yesterday, here were the big equations that we came up with. Q equals m delta t, specific heat. Q equals m, diffusion. Q equals m, latent vaporization. So basically, these two occur when you have a phase transition. This occurs when you have a change in temperature. Okay? So, one of the things you're going to do is you're going to make the calculations on what it takes to take water that's at ice, heat it up, melt it, heat it up, boil it, and then warm up to steam. So basically, if there's a change in temperature, you look up what material that you have. The specific heats are on that equation sheet. So, if it's ice, that has a completely different specific heat than water, which has a completely different specific heat of steam. Okay? Then, on these phase transitions, so if you're melting or freezing water, you're going to use this latent heat of fusion. If you're boiling water or any liquid, you're going to use latent heat of vaporization. Okay? Boom, there you go. So what you're going to do is you're going to find the energy it takes for each one of those, add them together. That's the total amount of energy that you have to dump in. Now, here's one thing that's common to all of them, and that's mass. So the more mass that you have, the more energy this is going to take. Okay, which should intuitively make sense. Okay, hey, I got a little mass, it's going to take a little bit of heat. I got a swimming pool that I need to warm up. That's going to take a lot more thermal energy. Okay, boom, there we go. All right, now, we talked about the gas law, PV equals nRT. Pressure, volume. This pressure has to be in what units?
Newtons per meter.
Pascals.
Pascals, which is the same thing as newtons per
Meter squared.
where volume has to be in.
Meters cubed.
N is your
Moles.
moles. R is your gas law constant, which is units of
Joules per mole.
Kilogram.
beautiful temperature has to be in Kelvin. Okay, got that. Life's good. All right. Life is good.
Yes.
Now, this would make life easier if you get out these lecture notes that I gave out. It's the actual lecture notes. So, what we're going to do is go through the changes on a pressure volume graph. So, if you do engineering, if you do thermodynamics, anything like that, you live and die by pressure volume graphs. Basically, a steam engine works because of the pressure volume graph. So if you look at the changes that occur, like with the syringe, okay, heating it up, cooling it down, all of this can be represented on a pressure volume graph. So we're going to spend a lot of time talking about this, and there's three processes that you're going to look at. An isothermal, and this is like on the bottom of the back side of the lecture notes. You're going to have isobaric, and then you're going to have isovolumetric. It's sometimes called isometric. Okay? So, if you think back to your days as squirrely little freshmen in your freshman science class, you were probably at some point given a map of the United States, and you had to go along and you had to draw lines that connected points of equal temperature. Anybody remember what those are called?
Isobaric.
Huh?
Isobaric.
Yeah, well, but if it's temperature, it's isotherms, okay? If it's equal pressure, it is
Isobars.
isobars. So iso means equal, okay, and not changing. So if it's an isothermal process, that means we're not going to change temperature. If it's an isobaric process, we're not going to change pressure. And if it's an isovolumetric, we're not going to change volume. Okay? So constant temperature, constant pressure, constant volume. Okay? So those are the three that we're going to look at. So we're going to start with isothermal, because if you can get isothermal straight, everything else becomes pretty easy to work with. Okay. So when you look at the units, so here you have pressure, which is going to be in newtons per square meter. Then you have volume here in cubic meters. So let's just say at the beginning we're going to draw a line across like this, and we're going to find this area. Okay? So if we find this area, what am I going to multiply together?
Meters squared.
Yeah, so I'm going to take newtons per meter squared times meters cubed. I get,
Meters.
otherwise known as joules. So rule number one is that the area underneath this curve represents work measured in joules. So the bigger this area is,
My pencil fell under your desk.
Just
But I
get it
can't- I
then.
can't. It's really far in there. I mean,
No,
I didn't
it's
remember
not. I
that.
can see it from right here.
hold on kids,
This is
It's,
what I-
it's closer to your side
This
than it
was
was
what
to
I didn't
his.
want to happen, is for everything to stop.
that's what you didn't want to have.
That's kind of why I motioned the kid behind them. Okay, just keep
Okay,
going.
what, did you expect Kendra to get it?
Well, I was gonna see if she had a
No, he
pencil.
expected me to give him one of my pencils.
Oh, I got you.
Yeah.
Wow.
Borrow
Yeah.
until I could get it after he was done
What,
talking.
we can trade her the paper that you borrowed?
I'm literally writing on graph paper right now because I forgot to put paper.
I just,
We had
I
this
gave you
discussion
so much
yesterday.
No, but you didn't
paper.
give us homework, so I didn't even bring my book back in last night.
Hunter, what happened to all that
this
paper
is
I
all my
gave you?
fault then.
Yeah, dude.
Okay, all
Can
right,
we just
anyway.
continue on with the
Okay. So,
Man, you're getting on my nerves.
so the bigger the area is, the more work that we're going to do. So let's start with that item. Now, I'm just going to make up some numbers. Let's say that we're at, I don't know, and let's say this is, okay. Now, because of the fact that we're working in pascals, and right now you're on a normal atmospheric pressure, you're under 101,300 newtons per square meter. That's like a big number to try and graph. So what we typically do is write this like times 10 to the 5th newtons per square meter. That way we don't have to write 100,000, okay? So this is basically like 1 atmosphere, this is a half an atmosphere. So this is like 0.5 times 10 to the 5th. 1 atmosphere, half normal atmospheric pressure. So here's the leap of faith that you have to take on this graph. This is volume that's in cubic meters. So let's say that I'm at 0.1 cubic meters, which would be about like EA, okay, 0.1 cubic meters, not very big. And then up here I'm at 1.0 times 10 to the 5th newtons per square meter. So this is basically, this pressure and volume is an X and Y coordinate system. So here's a volume, here's the pressure. So you can think of this as being an XY coordinate. But here's the odd thing, is that implied within this, and this is going to be important when you understand the graphs, implied within this is that there's a temperature that corresponds with this. So if I know a pressure and a volume, okay, I know that PV equals nRT. True? Home run deal.
Yeah.
So I can find the left side of this equation. Because when I multiply pressure times volume, I'm going to get the left side of the equation. So if I take 1 times 10 to the 5th and multiply that by 0.1, I'm going to get 1.0 times 10 to the 4th joules. So that's what the left side of the equation is going to be. Home run deal. That's it. Boom. Now, let's say within this, I've got 0.1 moles of gas. Not very much. I get 1/10 of a mole. I can let it be 1 mole. I'm just going to let it be 1/10 of a mole. Then I've got the R. So what I can find is the temperature that corresponds with this. So even though I have a pressure volume, I will always have like a third point of temperature, because with any given system, I'm never going to change the number of moles, and I'm going to never change R. So if I take 0.1 times R, I get, check my math, but I should get 8314, right? Because this is 8.314. I multiply that by 0.1, I get 0.8314. So this is going to be my temperature. So somebody take 1.00 times 10 to the fourth and divide it by 0.8314.
12,027.
What'd you get?
12,027.
12,000, let's call it 12,000, okay? Kelvin.
You right, Sam.
Alright, so.
Pretty big temperature, right? Okay?
Does
Pretty
that
big
even make
temperature.
sense?
So, huh?
Does that even make sense? Like, does that answer make like
Yeah, it could be.
12,000?
It's just, here's the point. It's going to represent a temperature, okay? I don't know what it is. Just, here's the point.
Okay.
Is that I can find a temperature that's going to correspond with this. Now,
That's pretty cool.
here's what I'm going to do. I'm going to start here, and the first thing I'm going to do, and this is the most complex one, because if you can understand the most complex one, then the simpler ones become much more easy to work with. So, what I'm going to do is I'm going to take this pressure, this volume, and I'm going to have it go through what we call an isobaric expansion. Excuse me, isothermal.
Berger, are you giving us the 0.1 or is it like a consistent 0.1 mole?
No, this is just 0.1.
No, like the 0.1 moles up there, the N.
Yeah, yeah.
You give that.
Yeah, I'd have to give that to you.
Okay.
So you're always gonna give that to us?
Yeah, you have to have that value.
Okay.
Okay?
That makes sense.
Now, so here's what's going to be important. If this is going to be an isothermal, here's what you have to look at. Okay? This is the key thing. If this is isothermal, is anything over here going to change? No, because I'm not going to change the number of moles, right? I'm not going to change R. Okay, that's the gas law constant. I'm not going to change the temperature because it implies that it is constant temperature. So you have to understand why this line curves down like it does. Because if you look at this, so what we're saying is that any combination of pressure times volume always has to equal the same number over there. Okay? It always has to equal the same number. So when I multiply pressure and volume, I'm going to get something. So as my volume is getting bigger, what has to happen to my pressure? It has to become smaller. So what that would mean, if you look at this in terms of a syringe, okay? So I've got this syringe at 0.1. I'm going to seal it up so that I'm not going to change the number of moles. So basically what's going to happen is that I'm going to pull this back, okay? And I'm going to increase the volume, but I'm going to keep the temperature the same. So as I pull that back, what's going to happen to the pressure inside the syringe?
Decreases.
It's going to become smaller because it's like I've got my room full of second graders and I'm going to make the room bigger. So therefore I'm going to have less collisions because the same number of second graders are going to have more room. Now, have I changed the kinetic energy of the second graders?
No,
No. Why?
didn't even do anything to it.
No, yeah I did. I made the room bigger. The temperature's constant. So I haven't given them more sugar or taken away the sugar. We're all at the same temperature. Okay? Now, this is going to boil down to signs. So here's what I want to look at. So on the bottom of this page, and if you actually need this, I will give you this equation, but I want to show you how it works. So at the bottom of this, on this back side, you've got this equation. Work equals nRT, natural log of VI over VX. Now,
I hate logs.
what?
I hate logs.
How
Sophomore year.
does it not change the kinetic energy if you're slowing those particles down?
No, I'm not. It's the same temperature. So the
temperature-
second graders are moving with the same speed,
Okay, just in a bigger.
just in a bigger area. Okay? All right. So here's what's going to be important on this. This is going to be N, which is going to represent the same N as before. So what does this represent? Moles. So this is in moles. This is going to be the same R, which is in joules per mole, Kelvin. Temperature is going to be in Kelvin. So basically, the mole is going to cancel out, the Kelvins are going to cancel out. I'm going to be left with joules. So this is basically the right side of the ideal gas law equation. Here's NERT, but now I'm multiplying it by natural law. Is this going to have any units? No. Why?
Because you're dividing by the same units.
Yeah, I'm going to divide cubic meters by cubic meters. Now, I'm not going to worry about this number for now. I don't know what it is. I don't care what it is. It doesn't make any difference. It's just going to be a number. But here's what's going to be important. In this case, my initial volume was 0.1 cubic meters. My final volume is going to be 0.5 cubic meters. So that's all I know, okay? My initial volume was 0.1. My final volume is going to be 0.5. So I've made this bigger. So here's what I want somebody to do. I don't just take 0.1, divide it by 0.5, and take the natural log of that. What do you get? I don't care about this. I just want this function. I just want this part of the equation. What'd you get?
Negative 1.61.
Negative 1.61. Now, here's what's important. Understanding thermodynamics is about understanding the sign. So in this case, I have a value that's negative. Okay? This is negative. Everything here is going to be positive. So if I expand this gas, okay, if I expand this, that means that I'm doing negative work. So if I increase the volume, I'm going to do negative work. Okay? It's going to be a key thing. I'm going to do negative work. Actually, the gas is going to do negative work in this case. Okay? Now, so here's how you have to view work. The other great equation out of this whole deal is delta U equals Q plus W. Now, at this point, here's what we have. I'm going to have a value of negative work. Okay? Don't worry about what that means from now. Just accept that this value is negative. Okay? It's a negative number. Delta U equals two things. It equals Q plus W. Q is the Q that we talked about before. That's the Q is the energy flowing in and out of the system. Okay? So Q is your energy flow. W is your work. W can be negative or positive. If the volume is getting bigger, work is negative. Okay? Because it's costing us energy. Now, delta U also equals 3/2 NR delta T. So this is the ultimate example of pure mathematical logic. In an isothermal expansion, what's the value of delta T?
It's the same.
0, because there's no change in temperature, right? I'm not changing the temperature. So if this is equal to 0, then notice this isn't temperature. This is important. This isn't temperature. This is change in temperature. I have no change in temperature. Therefore, delta U has to equal 0. So if I have a negative W, what does Q have to be? Positive, but opposite of? Now, beautiful. Now, here's how you can think of delta U. Delta U is your bank account balance. Okay? That's your bank account balance. So, visualize this. Upon my passing, I think Kendra is going to do great things. Upon my passing, in my will, I'm going to leave $10,000 to Kendra. Oh no! Wait!
That's on video right here.
Wait. Oh, yeah. But there's a big weight that goes with this.
Okay.
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 Gotta take AP Physics.
So, I'm going to give Kendra $10,000. So, if you think of this being Kendra's bank account, I'm going to put in $10,000. Okay? So that's my value of Q. I'm going to dump $10,000 into Kendra's bank account. Okay? But the rule is Kendra can't keep the money.
Dang it.
Kendra has to take that money and do something good with it. She has to do work. Okay? So I'm going to give her $10,000, but I'm going to say, but the caveat is, she only gets $10,000 once she says, this is what I'm going to spend the money to do to make the world a better place. So she's going to get an influx of $10,000, but she has to do good with it. So she's going to get an inflow of $10,000, but she's also then has to have an outflow of $10,000 that she's going to use to do work. So the delta T is going to be the change in Kendra's bank account. So even though she gets $10,000 in, what's the $10,000 going to be used for? Work. So your bank account balance isn't going to change. Okay? Now, what if I just said, I like Kendra, I'm just going to give her $10,000. You just get to keep it. You don't have to do any work with it. What's going to happen to your bank account?
It'll increase by $10,000.
It'll increase by $10,000, right? Because she doesn't have to do any work with it. Okay? Now, the other side of it is Kendra's a good person. Kendra says, you know, work camp changes will. I didn't get the $10,000. But I still remember that speech. I'm still going to go do $10,000 of work. Okay? Because I remember that speech. So, if she doesn't get any inflow of money, she still does $10,000 worth of work, what's going to happen to her bank account? It's going to go down by $10,000. Okay? So, Q can be positive, which is going to be the money that's transferred in or transferred out. This is the value of heat. So this is heat energy. This is work that's done, and here's this understanding prepositions is understanding thermodynamics. W is, in this case, is work done by the system. So here's what's happened. I'm going to take this syringe, okay? So imagine this syringe. So you have to visualize what has to happen in each case. So what I'm going to do is I'm going to seal up this syringe so that the number of particles stays the same. So here's how this would physically play out. I would take this syringe and I've got to add thermal energy to it. So what can I do to add thermal energy to this syringe? Yeah, put it over a Bunsen burner. Put it in a hot water bath. Something. Okay? So here, I'm going to dump energy into the system. But here's the kicker. This syringe has to be able to change its volume. So I'm going to dump the energy in. So this is like giving Kendra $10,000. But Kendra's going, oh, I'm going to do work. So that system is going to take those 10,000 units of money or energy, but then it's going to take that and then it's going to push against the syringe to make the volume bigger. So if Kendra keeps the money, that's like me dumping in the energy, but I'm not letting the syringe expand. So this concept of delta U is, this delta U is what we call the total energy that's in the system. So if delta U is going to equal to 0, which it does in this case, what has to happen is that if I have negative work, that means the value of Q is equal and opposite to that. But that is only true on isothermal values. I have no change in temperature, I have no change in U, Q and W have the same magnitude, but they're opposite signs. Okay? Now, if we reverse the process, let's say that I want to do an isothermal compression. Sounds kind of nerdy. Okay? I want to do an isothermal compression. So, if you go back, what's going to happen to my volume? Volume is going to become
Smaller.
volume is going to become smaller. So, so think about this. If the volume got bigger, work had a negative sign. So if the volume is going to become smaller, work should have a positive sign. So what's going to happen is that this syringe is going to get smaller, right? So if I go and look at this mathematically, when you look at this natural log thing here, these are going to get switched. So now I'm going to have a 0.5 over 0.1. So Eric, just take natural log of 0.5 over 0.1, otherwise known as the natural log of 5.
It's the same thing, just positive.
Yeah, so now I get a positive value. So now, by having a positive value, guess what? Now I'm going to have positive work. So if the volume is getting smaller, work is positive because I'm pushing these particles closer together. But here's the deal. In that situation, if I have positive work, guess what? Q has to be negative. Now here's how this plays out. Someone hacks into Kendra's bank account and transfers out $10,000. Okay? She's lost $10,000. Okay? Q is now a negative value. She doesn't want her overall bank account to work. So now Kendra has work done on Kendra. Because now it's like, okay, hey, it's a bad deal. Kendra got money stolen from her. Everybody's going to chip in and we're going to help Kendra out. Okay? So she lost $10,000, but everybody's going to do work to help Kendra out. So now that volume is going to become smaller. So here's how you can also think about this. Okay? Anybody here kind of get nervous in crowded places? Okay, Treadway, let's say that you get nervous in crowded
I don't
places.
like being incredible.
Okay, all right.
Just like being
So here's the deal. So let's say that we're going to put you in saran wrap. Okay?
Oh God, no.
Right? Stay with me here.
Okay.
And then we're going to put you into a sauna.
Ew.
Oh, no, but stay with me here. But we don't want your energy to change. So here's the deal. Energy is going to be flowing in because you're in a sauna. Okay? But you don't like being in this. So you're going to take that energy from the sauna and you're going to work against the saran wrap that's keeping you in closed. Okay? So you're going to get warm, but your total energy isn't going to change. Your temperature is not going to change because you're going to take the energy that's being put in and you're going to do work against what's trying to keep you enclosed. So that's what happens if I dump energy into the syringe.
But you're gonna feel hotter because you're working now.
Yeah, that's what I was thinking.
Okay, but here's the deal. But you're going to take that energy, okay, and you're going to do work against it. Imagine, okay, you're going to eat a candy bar and then you're going to work against it. Let's go with that way then. Okay? You're going to get an influx of food energy.
And then we're gonna go on the run.
And then you're going to go on a run.
We're gonna burn it off.
And you're going to burn it off so there's going to be no change in temperature. Okay? So if I take this and I heat it up, huh?
Change in temperature in the body?
Your body temperature.
Yeah,
Your
the
heart rate's
total
gonna be
internal
up.
energy of the system.
Heart rate's gonna be up.
I feel like you're gonna get hotter.
Okay, look, this is
physics, not biology.
Perfect guess. It's just an analogy. Okay?
Analogy means.
All right. Thank you. Now,
Not using like.
here's the other side of this. If I do a compression, now, what if I gave you a syringe like this, and I said, I want you to make the volume smaller, but you can't physically push on it. What could you do?
Decrease the temperature.
Decrease the temperature. Put it in an ice bath. You put it in an ice bath, you're going to take energy out of the system, but then the air pressure on the outside is going to push against it, and it's going to make that volume get smaller.
If we did that right now, would we even be able to tell the difference?
Oh yeah, with this you could. Especially if I had it really, really warm, and put this into like an ice bath, it would get smaller.
So
Yeah.
decreased temperature, increased pressure.
Yes.
Is that for everything?
Well, depends.
Okay,
Okay.
here we go.
So everybody cool with this? So here's the deal with natural logs. As long as you're taking the natural log of a value that is less than 1, it's a negative number. If you're taking the natural log of a value bigger than 1, it's a positive number. So here's what you have to understand right now. This is all I want out of this that you need to know. If work is positive, work is being done on the system, and the volume is getting smaller. If work is negative, the volume is getting bigger because the system is taking energy and is pushing against the atmosphere that's trying to keep it down. Okay? Work is positive, volume gets
Smaller,
smaller. Work is negative, volume gets
bigger.
bigger. Okay? On an isothermal expansion or compression, what's the value of delta U? Zero. Because there's no temperature. Got that?
Yeah.
Okay. Like I said, this is the most complex one. So if you understand this, everything else is going to be simpler to work with. So, but
Yeah,
here's
we
the,
definitely don't understand it, because like, we say we understand it
Yeah, and
now,
then we get
then
to
you have a
homework
question on the
problems,
whole
and it's
thing.
okay,
like-
let me ask you this. Okay, so here's the potential homework question.
Okay.
So, is it possible to dump thermal energy into a system and yet not change the temperature?
Yeah,
Yeah, if the
because you
work
can do
is.
work against, like, you
Yeah.
can work against.
If the energy goes to do
Work.
Work.
Yeah.
there, you understand?
The energy.
Okay, but then you
Hold on.
start putting numbers in there, and then we're like, what do we do with these numbers?
Okay, you only have N, delta T, and 2 volumes. That's it.
What?
Oh.
I'm sure you can
Yeah,
find a way to
yeah,
make that
I don't
impossible.
Wait, which of them?
Can you give us an example of it?
Which of them are
I
thermal
just
energy?
did.
But like with numbers, like give us, so write it at the top, like the
Okay,
numbers that
let
you
me
want.
get through all 3 processes, then I'll go through numbers. Okay?
Oh no.
Yes?
So is delta U just like the total amount of energy?
Yes, and this is
Like I
all
can
types
do
of
all
energy.
3.
Thermal, potential, the whole smash.
So we'd have to add it all together if you gave
The
us
whole
multiple.
You asked-
Yeah, but trust me, we can't. So here's what you want to look at. Okay?
The whole smash.
Here's what you want to look at.
The energy.
We can't, and here's what you have to understand with gas laws. When you look at what you can physically measure in this system, okay, you have to look at what you can physically measure. I can measure temperature. Okay, hey, I take the syringe, I drill a little hole, I put a thermometer in there. I can measure temperature. Hey, that's simple, okay? I can measure work because I can measure the initial and final volume of the gas. That's easy to measure. Simple. I can measure that. This, I can't measure directly. I can't look at this syringe and put it underneath a microscope and see all these little nitrogen and oxygen molecules running around going, okay, that has a value of 0.1. There's one that's like 0.5. Ooh, that one's going really slow. That's 0.001. Ooh, there's one on speed. It's 5. Okay? And I'm going to add all those together. Okay? I can't do that. But what I can measure is a change in volume, and I can know the number of moles. So what I do is I measure macroscopic measurements of temperature and volume that I use to figure out what's happening on an atomic level. So when you're measuring temperature, and temperature is an arbitrary scale. It isn't like, oh, you know, temperature is one of the fundamental forces of the universe. Temperature is something that we humans have made up. It's like time. We've made up time. We've made up temperature. So we arbitrarily figured out how to way to take a piece of glass to a substance and say, oh, if it goes up to this point, oh, you have a temperature of 98 degrees. Okay, it isn't a fundamental constant of the universe like big G is. Boom, 98 degrees. Oh, you know, Cubby's, or Bowie in this case, okay? Bowie's not feeling well. He goes down to the nurse. He goes, hey, I think I got a fever. Okay, nurse takes his temperature. Wow, it's up to 101. Okay, so that thermometer has measured on a macroscopic event what's happening inside of his body as measured by the kinetic energy of the particles that you're measuring. So when we're talking about delta U, it is impossible to directly measure delta U. We can measure work, we can measure the heat that's flowing into it.
And delta U is only kinetic energy.
And potential. This is the sum of all different types of rotational energy. This is the whole smash. Because when we look at nitrogen molecules, they're going to have some kinetic energy because they're moving. They're also going to have rotational because the atoms themselves are vibrating. So this is the sum of all the energies, which I can't directly measure. But so I measure big things to figure out what's happening here. Okay? Makes sense. Okay. All right. So we're good with this. Now, Stop that for a second. Okay, so here's what we've got.
I was trying to scare him.
Did it work?
Yeah.
I doubt it.
Yeah, he was like.
Okay, if you see it line like this, this is what type of expansion or compression? Isothermal. Okay.
Why?
This is really annoying my neck right now.
Isolating the
My dress.
I think the next one.
I'm gonna take my
On your jacket.
No, I don't have leggings on.
Just kidding. No, you didn't. Grass. Oh yeah, there is.
I have boot cuffs.
Okay, there we go. Now it's nice and
I
thermal.
feel like I'm choked. Oh, it's still recording. That's fine.
So pretty.
Who's all gone today? Guys, let's do a quick shout out. Who's all gone today? Meat is gone today. Caitlin.
Kale's always done that.
You say I say these things and then you
Good
say
luck
the
to you
same.
all in doing your homework. I hope that it's fun. Have a
Okay.
good weekend.
So, here's the deal. The reason that we have to use natural log is because this comes out of this being a curve. I can't treat this as like a triangle and go, oh, that's 1/2 base times height. Because of the fact that that pressure volume, okay, here is a constant because the nRT is a constant. So basically pressure times volume equals a constant. Since this is a curve, I can't treat it as a triangle. And the calculus is where you get this. So I can find the area underneath here using this equation. If I'm going this way, work is positive or negative? Negative. If I'm going this way, work is positive. Okay. Now, at this point, I'm going to go through an isobaric expansion. Isobaric means I'm going to hold what constant? Pressure. So at this point, I'm going to go from here over to here, right? Okay? Now, it's going to require a little bit of thought.
I don't like that.
But that's Friday.
Okay? Y'all can handle this. I have the utmost faith in you.
Whoa.
Utmost faith. Look at this equation. If I go across from there to there, what's happening to the pressure?
It's increasing.
It's staying the same.
It's staying the same.
Yes.
Because I'm at this pressure.
And the volume is increasing.
Yes! Okay. So, pressure is going to stay the same. Once I get over here, the volume is getting
Bigger.
bigger. Okay? What about my N and my R?
Constant.
Constant. So, if pressure is staying the same when I get over here, pressure is staying the same, volume is getting bigger.
So temperature is decreasing. Or it's
No, it has to
because
increase. Temperature would have to increase, because I have to stay up with.
Oh,
Yeah.
temperature has to get
Bigger.
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 oh, to compensate for the volume increase.
Yes.
Bigger.
Okay?
Shut up. He doesn't stop talking.
Annoying. Okay, now, so this is going to be a lower temperature. This point out here is going to be a bigger temperature. So, is my change in temperature going to be a positive or negative number?
A pause.
Positive, right? Now, look at this.
But your work's negative,
We'll talk about this.
right?
Okay? So, as I go across, I'm increasing temperature, right? So my delta T has a positive sign. Now, if you look at the idea that delta U equals 3/2 NR delta T. What's the sign of my delta T going to be? Positive. So therefore my delta U now is going to be a
Positive.
positive number. Oh! Oh! So I got a positive delta U. Oh, this is kind of cool, right? Now, delta U also equals what?
Q plus
Q plus
W.
W. Okay?
I'm
that's
sick
also
of
gonna
that
Q plus W. Oh! So, what has to happen over here?
Well, since it's increasing, doesn't W have to be
So
negative?
the volume is getting bigger,
So the
so
W
the
would be
work, by what we just said, had to be
negative. What?
negative or positive?
It's negative.
Negative,
Yeah.
okay? So, if work is negative, therefore, to
Q
get
is-
a positive delta U, Q has to be
Positive and
And
bigger than.
bigger.
Gotcha.
Now, okay?
So much is going on.
No, stay with me. Hold on.
Oh, okay.
Could I use this equation to find this area which would represent the work? Maddie, you were the first to go, no. Why can't I? This is a nice equation. It's got natural logs. I know my initial volume. I know my final volume. This is cool. Don't
Where is
ruin the
that on our
dream. But
sheet?
why can't, you're right, I can't use this. Why?
It's too easy.
You tell me right now. Tell me right now where that is on our sheet.
Dude, it's the first equation.
What is your?
Not that one.
Dude, it's not on that sheet.
Okay, yeah, well, this is one we have on the test.
I know. So if you need this, I'll give it to you.
Oh.
So,
Bailey has the answer.
why can't I use
Good old Stanley.
this temperature?
It's not that
It's not
temperature.
constant. The temperature is continuously changing. Oh, so I don't know which temperature to use because on an isobaric expansion, the temperature is changing. So I can't use this to find
I'm not taking.
my work.
Come on, Kim.
Okay, I gotta do it.
Oh,
Taking my goodness.
wait.
I think there's more.
Work also
Here's another one.
negative P.
I'm freaking tired of it.
Delta V.
Okay.
I'm so confused.
Now,
I'm telling the teacher on you.
Oh my gosh.
So how
Now.
does Stanley
Okay. Now, let's look at this. There's a negative P in front of this. Okay? Now, here's the deal. This is going to be whatever my atmospheric pressure is. Okay? So, it's going to be some pressure in newtons per square meter. Now, let's talk about this change in volume. That is not a change in velocity, it's change in volume. Okay? In this case, I'm going to start off at 0.1, and I'm going to end up at 0.5.
Negative word.
Oh! So now, I'm going to take 0.5 minus 0.1, which gets me
0.4.
0.4, which is positive.
Yes.
Oh.
But then we multiply that by a positive pressure, but then the whole thing gets negative. So therefore, I end up with negative work, because that fits with the idea that the volume is getting bigger. So that's the significance of this negative sign in front of this. Oh, but wait, there's more.
It's reeling you back in.
For an extra $3 if you pay the shipping and handling. Look, we're finding the area of a
Jules.
rectangle.
I said have a whole camera
Pressure by change in volume. So all this is a fancy way of saying here's the negative area of a rectangle.
Oh, like length.
Because the height is pressure,
Oh.
the width is change in volume.
Oh my gosh.
Treadway, my God, you make it look like a
Just
pure
Just
logic.
pause.
Wait,
Just
is the word
pause
is
and look
wait,
at
is
the
the
board.
word always going to be negative? Is the word always going to be negative?
If the volume is getting bigger.
Okay.
Like you know we're not gonna do that.
Okay?
Just pause and look at the board. Just look at this stuff
Crying in the
here.
middle of class.
Yeah, you tell me that's logical. Tell me
It is pure logic. If all you see was this, yes, it doesn't make any sense.
You're
But in
making
the
Bailey cry,
context of it,
everyone.
No, it's
Stop
Now.
making her cry. Everyone, stop it. She's gonna cry.
Okay, we've got to quit yelling. Shh. January's gonna have a moment.
Stop yelling.
Okay,
The poor fish is getting flustered. Oh, come here.
okay, let's decrease the energy in the system. Let's make delta U a negative number,
Okay, let's.
okay?
Dude, what does that even mean?
Down.
I don't even know what that means.
Eric is right there. Oh, Eric can't.
Delta U is the change in energy.
Now,
Somebody said that.
here's the question. This is why this makes perfect logical sense. Could I use this equation on an isothermal expansion?
No.
No.
Okay, it's not a rectangle. Do I have a change in volume?
Yeah.
Yes. But
Your pressure is
my pressure changes. So this is why I can't use this on an isothermal, right? But I can use this nRT natural log because I have a constant temperature. I can use this one on an isobaric expansion because I have a constant pressure. Okay? Makes sense.
Makes sense.
So here's the deal. So let me draw this again. So if all I have is this, I'm going from this point to this point. What's going to happen to the temperature?
Increase.
We're going to have a positive delta T, right? True? Okay. Now, work is going to be a positive or negative number? Negative number. So this is going to be some negative number. My delta U has to be a positive number, and that's a positive number because I have a positive change in temperature. Yes?
So I thought if the temperature's decreasing.
No, the temperature's increasing.
Okay, yeah, but so then shouldn't the pressure be getting smaller?
Because this is
It's an isobaric expansion.
Pressure
Pressure
remains
stays
constant as the volume increases.
So when temperature increases, pressure doesn't decrease.
Hold on. Just give me 1 second.
This is like
You're trying
Easy
to come up with general rules that you can use all the time. There's 3 different processes going on here. Okay? So here's the deal. Delta U also equals Q plus W, right?
Yeah.
So my work is going to be some negative number. True?
Correct.
So therefore Q has to be a positive number that's bigger. So I've got to have a bigger positive Q to get a positive delta U. So here's what this means. I'm going to leave Kendra $10,000. Okay? But she only has to do $3,000 worth of work.
It makes a net profit of 7.
Yeah, so her bank account's going to go up because of the fact that she only has to do $3,000 worth of work.
And she puts
And it's
that,
like the trust fund.
no, she puts that $3,000
In a mutual
into
fund.
a treasury bond that is inflation exempt, and you know, at the end of 10 years, she comes out with a yield of 7%, and you're looking at a pretty nice profit there.
Okay.
So Kendra,
Of 7,000 or the 10 originally.
All right.
I mean, why not put everything in?
Okay, no, because she has to spend
Because she
some
has to
money.
spend
Yeah.
money.
Some more.
I know, that's what I'm saying, like,
Okay.
put the,
Why don't you just
put
pay her
even-
Now-
15?
So here's how this would physically happen, okay? And you have to be able to visualize this. So here's this syringe, okay?
Okay.
Here's the syringe. I'm going to put a little temperature gauge in here, right? I'm going to have to dump thermal energy into it, so what am I going to do? I'm going to heat it up. I'm going to put it in a hot water bath. What's going to happen to the volume?
Increase.
Volume's going to increase because I'm going from a smaller volume to a larger volume. Okay? But unlike an isothermal line, the temperature is going to go up. So I'm going to dump more energy in than what I use to do work. Okay? Does that?
Oh, I just made another connection. It's okay.
Okay, good. All right, I like these. That's a good thing. So, now, let me ask you this question. Okay, so here's the question. I can start here and go from 0.1 to 0.5. Okay? Situation number 1, I can do an isobaric expansion where I have a constant pressure. Situation number 2, kind of going with the fuchsia color since I'm wearing salmon today. Okay? Alright? I can do an isothermal expansion. In both cases, do I have the same change in volume?
Yes.
Yes. Same change in volume, right?
Correct.
In which situation do I do more work? Nope. Do I do more work with an isobaric expansion? Do I do more work with an isothermal expansion? Or do I do the same amount of work because there's the same change in volume?
These questions. I'm going to go with the purple line.
Then you think that's going to be more work.
The volume is the same.
So how many vote the purple line? 1, 2,
Raise them high.
3.
I'm proud, guys.
How many vote
The other one.
the top line?
Dive in.
Okay, or that. How about it's the same because there's the same change in volume.
Reese didn't vote.
I'm thinking about it.
3.
Kendra, vote.
I'm thinking about it.
Okay,
Okay.
well, you don't have time to think. Just answer.
It looks like it should be pretty simple.
Just vote.
It is. It is extremely simple.
Yeah, thanks.
That's just gonna make us
Now,
feel
after I
really
listen-
bad.
Does it have to
I think
do
it makes
something about the
sense,
area?
Oh, it has everything to do with the
Yeah, it has a
area.
working
Okay, yeah.
area. When the
Yeah.
There's
In
so
which
much.
situation is the area bigger?
The top.
Yeah,
The
that was
top
so
line.
simple.
This area is a lot bigger
Just
than
sitting there
this
roasting
area.
us up there. Not even like.
What? What was it?
No, oh my god.
That seems way too easy.
Yes. Just look at the graph. This area up here is a lot bigger than this area down
Yeah, you're wrong.
You said the same.
Yeah,
So
since
this
when
takes-
does pressure times volume equal work?
here.
Since today,
Since today.
Now, if there would have been a forced distance graph, I would know.
Okay, it's a forced distance graph. Which one has more work done on it?
Obviously, the top one. It's a bigger space.
Yes.
Okay, well, I was not made clear.
Yeah. I remember when work didn't equal.
Okay. We got this
Oh my
one.
god.
I think.
Now,
You have an
the last
isometric
one's the
compression?
easiest.
What? Right? You
What?
have
Is it-
isobaric
is it-
compression,
what?
didn't you?
I really
so if
don't.
I
I'm thinking
reverse
if
this
they're
and
like
go across
putting an equation that takes the whole board.
Yeah, so if I go across this way, work's gonna be, Q's gonna be,
Negative.
delta
Work
Q's gonna
equals
be
0.
negative. Because I'm gonna drop
So
my
when you go
temperature.
left, work is negative?
Yeah, because I'm making the volume smaller.
It's positive.
If I go bigger, the volume gets smaller, work is positive.
I was saying sorry.
Okay, if the volume gets bigger, it's negative. It costs you energy to
Me
make
or
it
the other
bigger.
one.
Okay?
I speak Duckanese.
If it's smaller, work is going to be done on it, so you're compressing it. Okay?
Okay.
Got that?
I speak Duckanese, boy.
Good, I'm happy. Now, the last one's actually the easiest. Okay? So, got another pressure volume graph. So let's say I started in here, and I went across, had an isobaric expansion, right? Okay?
Hurts my head.
Now, at this point, I'm going to bring this line straight down. Take the hand. It's rude.
No,
Okay.
that is good.
So, I went through an isobaric expansion, and now I'm going to drop this line straight down. What is staying constant?
Pressure.
Volume.
Volume.
Volume. So this is isometric.
How is
Okay?
pressure staying constant when
It's not. This is constant volume.
okay, for the black line, not for the straight.
volumetric?
Isometric, isovolumetric is the same thing. Depends on which book you look in.
Okay.
Okay?
So just for the black line it stays.
No, Grant, agree.
Okay. So, let's start at the beginning. Delta U equals Q plus W. Okay? How much work is done?
None. There's
None.
not an
Why?
area. There's no like area.
There's no area. What is it changing?
Thanks. Volume.
Volume. Oh.
I don't understand what's going on.
Work equals negative P delta V. If I go from here to here, what's my change in volume?
Zero. So your work is
How
zero.
do you get a change in volume but not a change?
That's only.
Volume isn't changing. It's a straight line.
I want to make those like paper snowflakes. Do you guys know what I'm talking about?
Let's
You
go
just
from
cut them
five
and
down to
they're all the
How
same.
is the pressure changing?
It's not changing
You
at
get
all.
like a
Something's
square piece of
changing.
paper and then you start making
Yes,
designs.
the
And then
volume.
you can flip
Okay,
it out.
how's
And
the
then,
Oh, so you
volume
make
isn't
Yeah, like
changing.
Everyone's yelling
I think we should have that next.
like you know Elf, like the movie Elf, when he
Look.
decorates the whole like
Okay.
store.
Yes.
That's
We'll,
what
we'll get
We
to
should make
pressure
this
in
I was
just a
drawing some on
second.
my paper and I just.
So, Garfield,
Alright.
let's just focus on the volume. We'll deal with pressure later.
Alright, so how's it changing?
Okay? So, as I go straight down, I'm keeping it at 0.5. So in other words, I'm going to take this syringe and I'm going to lock it in place so the volume can't change. Okay? I can't change the volume.
Unless you
No.
No.
Not going to change the volume.
Okay, you're not gonna
Don't
change
put
volume.
any.
Alright,
Wait. No, this volume isn't going to change.
Alright.
Okay. So if I look at this, what's the value of delta V? Zero. So therefore, there is
No work.
no work. Now, if we use the other one, nRT natural log of VI over
Oh, you're
VF.
just showing us that these equations don't work.
Yes. What's the natural log of 1?
I don't know.
Zero.
Zero.
Okay.
So no matter how you try and calculate the work on an isometric change, there is no work done because there's absolutely no change in volume. So if you take the natural log of 1, you get 0. If you take a change in volume, that's 0. So there is no work done.
Is there a reason you're calling it isometric instead of isovolumetric?
It's just depends on which book.
I think we already discussed that.
Okay? Now,
Grab it.
so
Ew.
at this point, what's the value of W?
I don't know.
Zero.
So my change in energy is only going to be caused by Q,
What's Q?
right? Now,
Of energy that you put in.
let's look at this. PV equaling nRT. As I go from here to here, what happens to the volume? Volume
Stays.
stays the same. Same volume, right?
So the pressure would then probably stay the same.
So, no. Oh, Skippy.
I was just making sure.
Okay.
He was just throwing
That's
you.
depending
If
on
I
the
go
temperature.
from
He was just
here,
throwing you a curveball.
if I go from here to here,
And you hit
what happens to the pressure?
Goes down.
It goes down. So what's the only way the pressure can go down?
If the temperature goes
If the
down.
temperature goes down. So I'm going to have to lower the temperature. Okay? Now, think about this. I've got this syringe and I've locked it in place so the volume can't change. What would I do to lower the temperature inside the syringe?
Temperature.
Pull it.
I can't change the volume.
You're gonna have to put it in an ice bucket.
Yeah, I can put it in an ice bucket. So which direction is energy going to flow in terms of the syringe? Is it going to flow out or is it going to flow in?
Out.
Flow out.
So the pressure therefore would decrease.
Yes! Because the
We're
particles
done.
inside are losing kinetic energy.
End it now.
But no work is done.
But no work is done because the volume doesn't change.
Who knows?
Oh.
Ooh.
Woohoo! Can we put a little filter on right now?
Now, hold on.
Oh, wait.
Oh no,
What
what?
is it?
I don't know what we did. Hold on, it's still on.
You're still.
Now,
Wait, no. That one?
Sparkles.
delta
Sparkle it up.
U equals 3/2 NR delta T.
No.
I go from here to here, what happens to the temperature?
It
It decreases. So therefore my change in temperature is going to be
negative.
negative. So therefore my delta U is going to be
Negative.
negative. So I'm gonna have a negative delta U. I have no work, so therefore Q has to be a
Negative number.
negative number. So I'm gonna take energy out of the system, I'm gonna cool it down, but I'm not gonna change the volume. Treadway.
So the graph for this is literally just like a vertical line.
Yes, that's it, it's a vertical line. That's it, boom,
Cool.
So it's not even really a graph.
I can do that.
it's a line.
I mean, it can be a graph because
Okay,
there's no
yeah, but
area.
it's at zero. Or-
Okay,
That's what I'm saying.
by that definition, this isn't a graph either.
No.
No,
Wait, so how'd you get the area if you're?
If it's a vertical.
yeah, there's an area.
Oh, that's what,
obviously.
oh, that's what, no, that's only when pressure and volume change, so you can make a cool line like that.
It's a dashed line.
Oh, see. This is where I was confused. You drew that line up there so it looks like a box. You
But-
should just erase the pressure line
Yeah,
altogether.
yeah, that's.
And
No,
put a
I was
dot.
just saying.
And put a
No,
dot.
erase it, erase it.
He was saying that it started off and then it.
Yeah, I started here, went through an isobaric, so in other words, I
Right.
took it
Drawing
at
a
point
little
one.
line.
Right, but I was just
I made
confused.
the volume get bigger.
Yeah.
Now, I'm gonna lock it in place.
So there was a change, there was work done when it was.
Yes, I had negative work done getting to this point. Okay? Now, I went from here, over, and then down. What's another way that I could get from here to here?
An isothermal change.
Yeah, I can draw
Jeez.
fast.
Okay,
Yes.
so
It's like a flower.
if your straight line goes upward, you have a positive
Yeah,
delta U.
so if I go from here
positive
up-
U. You got positives then.
Yes.
Well, isn't it still zero?
Yeah, there's still no work done.
Okay,
So
so
here's what
pressure-
would happen.
It's a
pressure is not
positive zero
changing
instead
and
of a
volume
negative
is not
zero.
changing.
Visualize this. I'm going to take this syringe locked in place, and I'm going to put it out in the sun where it's going to get hot.
Yeah.
But I can't change the volume.
Oh, pressure.
The pressure is going to go up because the temperature is going to go up. So the particles are going to have more
But the
and more
system does
kinetic
no
energy.
work, which is
But
why.
there's no work.
Which is why the pressure increases, because it can't get rid of that.
I
Yes.
think it's a bird.
All right.
Alright guys.
Can we honestly just call it
Yes.
quits now?
So if
No,
the temperature
we're not
increases, then the
done.
pressure
Is that what you're
increases.
saying?
Yeah.
Okay.
I mean, if it could
But literally, there's only three
I think I should
possibilities.
just throw them a flower.
You either keep temperature the same, you keep volume the same, or you keep the pressure the same. That's it.
And in the case of pressure or volume being the same, we don't even have to worry about it.
Because there's no change in volume.
Where'd you get gum from?
Okay. All right, so stop that. I know. Okay, so there's some conversions up there on the top. So let me kind of take you through what those conversions are. When you look at how energy was initially measured, and this is where the term calorie comes from, they used to think of calories being like a set value. So like where that term came from, like when you would burn like wood in a fireplace, they would view a calorie as being, okay, that wood has a certain amount of calories. When you burn up all the wood, it's like a fuel tank that goes empty, okay? So what they would do is they said, okay, if I take that wood, and if you probably, some of you might have did this lab in biology, where you take like a Dorito chip and you light it on fire and you burn it and then it heats the water. Anybody ever do that one?
I've done it 3
I
times.
think I burned a Cheeto.
A Cheeto, whatever.
You take
Okay?
the Cheeto,
Some people use almonds,
light it on
whatever.
fire.
So what they would do is they would measure how much the temperature of the water went up. And that's how they defined a calorie. But here's the problem. There's two different types of calories. There is what we call the food calorie, which is an uppercase C. And then you have the actual calorie, which is lowercase c. Here's the problem. If you look at like in the sample, you have an Almond Joy, and the Almond Joy says that you have 230 calories. That's actually what I was typing in the problem. I was eating an Almond Joy. That's what that means. Okay?
Dude, dude, there's no way.
So, if you look on an Almond Joy, it's going to say that it contains 230 calories. But here's the problem. In terms of the original definition of calories, it was actually 230,000. Okay? Lowercase calories. This is the
so
actual
it's just
definition of the
times
calories. So the food company people were flipping out going, my God, we cannot let these people know that there's 230,000 calories in a candy bar. They're never going to eat it. So they said, oh, we'll just drop off the 3 zeros at the end, make it 230. That's much more tolerable. So people can handle 230 food calories, but they flip out if you realize, oh, that's actually 230,000 calories. So, yeah, so basically, they just lopped off the last three ends, the last three zeros. So, and when you talk about efficiency, human beings are about 25% efficient. So what that means is if you consume 100 calories, you only functionally get to use about 25 of it. The other 75% is burned off basically because you all are little thermal ovens, okay? And you're burning out carbon dioxide and water vapor every time you breathe out. Your car engines are also about 25% efficient. So when you buy like 100 gallons of gasoline, you only functionally get to use 25 gallons of that. The other 75 is lost in the form of heat.
Oh my gosh, that makes me so mad.
Okay. So when you get to questions 2 and 3, actually 2 all the way through 7, those are all based upon Q equals MC sub P delta T. Okay? You're going to look up the specific heats of water, copper, iron, whatever that is.
Would you say that equation one more time?
It's
Oh wait,
Q equals M delta T C sub P. It's the one that's on the back of your sheet.
Piece of pizza.
Yes.
You want a piece?
Now,
You said like M delta TCP.
Piece of pizza.
okay.
Pepperoni.
Now, when you get to number 8, on number 8, you're going to have to do a total of 5 different calculations. 3 of them are going to involve this. 2 of them are going to involve Q. Well, one of them is going to be Q equals M latent heat diffusion. The other one is going to be M LV. So on that one, you're going to use this one 3 times, this one once, this one once. Okay? And then you're going to add them all together.
To get
Yes. Well, actually, you're getting Q. Because it's that. Now, when you get to when you get to 9 through 17, 9 through 17 are all about pressure volume graphs. Okay? They're all about pressure volume graphs. Pay attention to the units. 9 through 17 are all about PV graphs.
And those
Okay.
equations behind you, does L equals length? What?
This is latent heat diffusion.
Oh,
This
yeah.
is latent heat vaporization.
Okay, you can
Yeah,
see
it's
where I
not
went
that
wrong.
big.
It's not like that much of a massive stage.
obviously we saw.
I honestly didn't know that. That's why
Yeah.
I'm
I
glad
didn't
you said
realize
that.
it though, and I assumed you would.
Wait, what is Layton's? Oh, it's right here.
Oh, look, it's right there. Wow, it's on your chart.
Wait.
It's also defined on your equation sheet.
Oh, yeah.
Okay,
Layton's heat
we're done.
Q equals MLF.